Hello, everyone. Alfred Cromwell here, the founder and president of City Tutoring. Before we begin on this with the lesson today, I have an announcement because we often hear these days of most of the stories you hear about students today are really awful. We hear about disrespect in the classroom. We hear about disobedience in the classroom. We hear about profanity in the classrooms, defiance of authority. We hear all these things, but rarely do we hear of good stories that come up because I am pleased to say that not all our young people are, it would be a cliche if I said, and it would be very ignorant if I said that every single young person in America today is corrupted or is defiant in any way or disrespectful. And I was just reminded of that this morning because at City Tutoring, our students apologize. Not only do our students apologize, but they also take accountability for if they do something wrong, they make sure to take accountability. We make it very clear that one of our distinctive values at City Tutoring is that we are not like the rest of the many of the public schools in this country. The public schools in this country don't teach anymore things like accountability. They're too busy doing political propaganda for the Democratic Party, and they don't care to actually instill the values of success in our young people. If I could have one hope in my lifetime, if I could have one hope in the education world in my lifetime, is that all the public schools in America would shut down unless they take radical action to clean up their act. So I'm going to share with you a letter that a student wrote to us this morning because she had missed a required review session. She's a remedial student, by the way. She's a remedial student. And she was just very, very repentant about what she did. And I'm going to share with you her beautiful message to our, not, it wasn't addressed only to me, it was addressed to staff as well. She said here, to the staff and administration of City Tutoring. My name is, and of course I'm going to omit her name. We respect privacy as well. And I am scheduled to take my such and such exam on Wednesday. Well, I'll omit the date just in case because it's a known exam. Unfortunately, I did not attend the first required review for math because I did not properly check my email for that date. That morning, I also had an emergency situation and with my family. My little brother had a stomach virus and I had to take him to see a doctor. However, if I had known about that review, I would have had a family member or some kind of childcare plan and joined the first review session. I understand, and emphasis mine, I understand that this is not, shall I repeat that? I understand that this is not an excuse because I should have been up to date with all of my emails. I attended the second review session on, of course, she gives a date, for English literature. And I will be looking forward to the next one we have available. I also attached a letter from the doctor's office in regard to my brother's appointment for that morning. When I first set foot into City Tutoring, I felt a fiery determination in accomplishing my goals. Prioritizing is the key to be successful. I take full accountability for missing the first review. Sincerely, and she signed away her name. By the way, for those of you who were wondering, she is only 16 years of age. She's only 16, and already she shows accountability. She has a good attitude. That's the kind of student we want to see at City Tutoring. We don't have time for the sassiness and the disrespect and the entitled attitudes that we see all across this country these days. So I feel so blessed to be surrounded by young people who take their studies seriously. I've never had, I'm always very honest with you all. because if I weren't honest, I would be disrespecting my audience. And I know every single person who has subscribed to this channel, you value truth. That's why you subscribe to the channel in the first place. One of the things I will tell you is that I rarely can I tell you in my over 20 years of teaching both level. I teach mostly college students, but also high school. Nowadays I'm getting a lot more high school people because the nature of tutoring. But I cannot name more than two or three, if I recall correctly, in instances where I have had a student who was disrespectful to me. I'm not saying it couldn't happen, but I think I am a firm believer in the philosophy that you are also very much influenced by what you give. In other words, even though there will always be sassy people, even though there will always be disrespectful people, we see them sometimes in the comment section. We have clowns come into this channel, very rarely, but they're there. They troll. They type. You can even see it in their grammar. It's ridiculous. But the fact remains that if for the most part, if you are an honest individual, if you are a serious individual, most normal people will take you seriously as well, including young people, including most teenagers, if we want to call them that. Of course, we have a lot of nutcases. There's a lot of nutcases in America, and so of course we have people who are unhinged and do not respect others. They don't even respect themselves. So how can they respect other people? You see them all the time, drugged up, drunk, high, and of course if they don't respect themselves, how do you expect them to respect you? You can only get respect when you start respecting yourself and when you start taking personal responsibility for your problems. So I am very blessed. Praise God that I have a student like that I have students like that, I should say. You're going to see next week, by the way, probably. I've mentioned this many times. I'm already in contact with a student wants to come forward on this channel, and she really wants to give her testimony about what her experience has been. And I have many others too. But, sometimes they don't want to appear on camera because, they know I have thousands of people now, thousands of subscribers. So they're a little bit shy. But this young lady you're going to see next week, she is not shy. And she started out as a math failure. She had a bad attitude. She had everything. You're going to see on the channel, you're going to see her talk about how her life was turned around by the methods of City Tutoring. She's now working successfully. She's doing a good job now somewhere. And she's still studying mathematics. And she said she was very much inspired. What brought her over to City Tutoring, she was inspired by the biography she read, the one that I wrote called Mathemachicken to Mathematician. So I just thought I'd share that with you. So anyway, we're going to talk about sets now. We have to talk about sets. So if there's one foundational truth that underpins all branches of mathematics, besides the fact that we know that reality is objective, it's really set theory. We really have to talk about set theory. We've already seen the absolute necessity of set notation when we were dealing with quantified statements. You saw that in the previous videos. The quantified statements, we were referring to the kind of precise, logical thinking that used to be valued before this age of my feelings rather than my thoughts. Now, before anyone panics, we're not about to embark on some tedious ivory tower journey into formal axiomatic set theory, mostly because if I were to do that, it would actually be a separate series, not because I'm against it. It's just that we're doing logic, we're doing mathematical logic, and formal axiomatic set theory is a branch in and of itself. It's something to be studied independently. I can give you, though, towards the end of this series, and it's going to take months because there's a lot to say, I will give you a taste of axiomatic set theory as well. But that's the kind of thing we need. And we're going to take in this video a practical, no-nonsense approach. We always take a no-nonsense approach, and we're going to cover only the aspects of set theory that actually matter in mathematical analysis. So this section, we've already covered the equivalent to one chapter where we talked about quantified statements, disjunctions, conjunctions, and I showed you the symbols. and you need to have the prerequisites. Remember, watch all the previous videos, or otherwise this video will make no sense. So in this chapter, we could call it chapter 2, I guess, we really need to talk about set theory. So in this video, we're going to talk about what a set is, the basic notation of sets, because even in mathematics, good fences make good neighbors. And then after we finish that, there will be other sections. We're going to have a sections 2 and 3 in a separate video, of course, where we will talk about relations and functions. Essentially, how different sets interact and behave. Unlike certain people who refuse to acknowledge any structure whatsoever. Now, we then have section 4. And in section 4, we will be comparing the size of sets, especially infinite ones. And yes, infinity comes in different sizes. Much like, hopefully not in imitation of, but an analogy could be government overreach. We have a lot of that in America these days. Hopefully it goes down in the next several years. And then finally, the 5th section we'll talk about is we might do a brief dive into the axioms themselves of set theory and some of the thornier problems they create. So if you enjoy deep existential questions like whether math itself was discovered or invented, then you've come to the right channel. And as I always say, if you have a short attention span, if you're the TikTok type, if you're the you can't read more than a paragraph, if you're the TL/DR type of person, you don't belong on this channel, because you're not going to understand. You're not going to last on the channel. And by the way, if you have a short attention span, you will not be successful as a mathematics major. It's just not going to happen. So you may as well thank me for telling you the truth, because if you're the type of person who you're not willing to put in the hard work, you're not willing to understand, you're not willing to ask your professor questions, you're not willing to go to office hours, you're not willing to do the work that it requires, don't even bother to major in math. Save your money and do yourself a favor. All right, so let's start defining what a set is. Let's go up to the board and figure it out. All right, so we have to discuss sets. We really have to talk about it, because we really haven't been defining them, and it becomes very important as we progress in this series. So, in the civilized world of mathematics, we use capital letters to designate sets. And we use this symbol, the elements, and you should have watched my previous videos for that. But yes, we're talking about something called membership, a concept that once upon a time people understood to require actual qualifications. So when we write, for example, that something is an element of, we mean that that object is a rightful member of the set. And when we use the symbol, it looks like an E with a slash through it, it means that it has rightly, based on the definitions we are using, been excluded. We shouldn't shy away from exclusion. It's not a bad thing to be exclusionary. So it's just the cold, hard reality of whether you belong or you don't. And it's okay. Now, when we sort out sets, and again, I recommend you watch my previous videos, which are in this playlist on the symbols that you need. So have a look at this, right? The set A, we're saying that it's a capital letter A, and we always use braces when we are distinguishing sets, when we are defining a set and including the objects. So here we have 1, 2, 3, 4, and then we're saying that 2 is an element of set A. Of course it is, because it's in there. But we're saying 5 is not an element of A. Sorry, 5, better luck, if we can use that term, next time. Now, in order to avoid complete anarchy, we must insist that a set be defined by a clear and objective property. Often called, if you use a rule, it's called set builder notation, by the way. This means it should be an undisputed fact whether an element belongs to a set or not. What we don't require, however, is that people actually know the answer right away. If you are ignorant of the truth, it does not change the truth itself, despite what some crazy nutcase professors in some universities might tell you, especially in the humanities. Now, another way of putting this could be for any element A and any set A, the statement, if you say A is an element of set A, it must either be true or false. You know very well true and false can never be both at the same time. There are no gray areas here. No, it depends on your perspective nonsense. As I've said many times, as a cliche, the reality, the facts, the truth, they don't care about your perspective or your feelings. So let's see if the following, I want to mention a few more things because I drew here. That U symbol is called the union of sets, by the way. Be familiar with it. We're not going to talk about it just yet, but be familiar with the symbols. Also, the upside down U is the intersection of sets. So we have the union of sets and the intersection of sets. The intersection of sets is when two sets or more sets share some element in common. Now, have a look at this symbol here, right? This is a problem that causes lots of confusion for our students because this is called the empty set symbol. An empty set, as you recall from the previous videos, it means something that does not really, is not in the set, right? But the empty set is different than the set containing the empty set, just an empty box, right? When you have in the second example, you have an empty box in there that contains an empty box. So it would be really a mistake to think about this symbol as being nothing. It is something. It is a set. It doesn't have anything in it, though, but it's still a thing. That's the first thing to take into consideration. The second example here, the one within the braces, this is what is denoting a set containing one element, and its element is a set which contains no elements, but it's still there, and it's still a thing. So you got to be really careful with that. And oftentimes, another way to look at something is you can think of a set as having elements, of course. And if you want to define it by a rule, you need the conditions that are used to generate those elements. And this is what we were talking about before, that were set builder notation. So some examples of that would be something like if I gave you n squared, and we're going to say n squared is an element of the natural numbers. It should be an open n, but I think you know what I mean. It's the natural numbers. So one example would be like 1, but we're going to square it, right? So then 1 squared is 1. We need natural numbers, right? 4, 9, 16, 25, and just keeps on, right? Or if I gave you, let's say, the absolute value of n, and this time n is going to be an element of z. Now you remember, we talked about these letters before in one of the first few videos about the symbols that you need to be aware of. So I'm assuming that you've watched those if you're watching this video. All right, so the absolute values could be the integers 0, 1, 2, 3, and so on and so forth. So in the first case, it uses the condition. We're saying that n is an element of the natural numbers, which means that you should plug in 1, 2, 3, 4, 5. Now, some mathematicians defend, and I've been tempted to as well, but I'm not going to do it in this video. Some mathematicians consider zero, and I oftentimes struggle with this, a natural number. But I don't want to confuse anyone, so I'm just going to put it as how most of you learn it. Now, the second form here is we're using the rule that was given to us as well. So we have to be very careful with the notation and with what is being asked. The other thing to take into account, the other thing to mention is you see those three dots I have there. Dot, dot, dot. Be careful with your dot, dot, dot. It's often used to mean that something that some kind of sequence goes on and on forever. But you have to make sure that the pattern is clear. For example, if you used the numbers 1, 2, and you indicated to me without specifying anything, I'm going to put it on the board here. What does that mean? I've had students do that too. Does this mean an arithmetic sequence? Does it mean 1, 2, 3, 4, 5? Does it mean a geometric sequence? 1, 2, 4, 8, 16? Is it a sequence of factorials? 1, 2, 6, 24, 120? Perhaps the Catalan numbers? 1, 2, 5, 14? What does that mean? You got to be real careful with this sort of thing. Now, I wanted to show you a couple of other examples. Some questions for thought. Which of these, according to what we have been discussing, we said that that a set is a collection of things we call elements. We also said that you have to provide, it has to be well defined. You have to have some kind of definition. So have a look at these and let me know what you think. Pause the video. All right, so let's take the first one. Hopefully you paused the video. All the current U.S. senators from Virginia. It's well defined. Yeah. Although some may argue whether they qualify as a distinguished group. I would not call any senator today a distinguished man or woman, for that matter. I cannot think of a single senator these days, at least not off the top of my head, and certainly not the ones representing Virginia, who are in any way worthy of any kind of respect, based on their actions, based on what they say. The other, but it is a well-defined set and the reason why is because we can actually name them. We know who they are. The second example, B, we have all the prime divisors of 1987. Well, that's clear. It's factual. So we can also call that a well-defined set. But notice the third, all the nice people in Canada. Well, that's vague, it's subjective, and thus it's unworthy of serious mathematical consideration, much like modern university policies. We don't know what the word nice means. We don't know at all, actually. Unless it's defined to you, that's a very subjective term. What about D? All the prime numbers between 8 and 10. All the prime numbers between 8 and 10. Ah, there you go, the empty set. Doesn't exist. All right, so when we indicate particular sets, we need to indicate the property that characterizes its elements. When you are dealing with finite sets, this can be done by sometimes you could just list the members. If I asked you, for example, for the numbers between from the numbers from 1 to 4, you would list them out. That's called roster notation. So you do 1, 2, 3, 4. You also have descriptive. If it's descriptive, that means that you actually give a rule. So we're going to be dealing now with the definition, right, which is the sort of how the hierarchy of sets. All right, I decided to also include here for this lesson. These are examples of sets that you should already, if you're not familiar with them, you should definitely become acquainted with them if you're serious about your math. The first one is the set of rational numbers. It's an open Q, and you need to start training yourselves to read this. If you read this out loud, it says the rational numbers are defined to be the set of all fractions of the form a over b, such that a and b are integers, must be integers, and b is non-zero. Notice the restrictions. Another set that you should be familiar with is the 2 by 2 real matrix. And this is A, B, C, and D, and they are all elements of the real numbers. You also have a lot of students are not familiar with this one, and it used to be taught many, at least in my day. It's real number symbol squared, and that is referring to the XY plane. The ordered pairs of real numbers are extremely important. So x is an element of the real numbers, and y must also be an element of the real numbers in this context. And then we have the unit circle, right? X and y are elements of the real numbers if you can read this as, it's really the set. It's inside of r squared, right? So it's contained inside ordered pairs. Very important property. And of course, it's x squared plus y squared equals 1. So the next one is what we call the closed interval, right? It's the one that has the brackets. And of course, x must be an element of the real numbers. And that means n is less than or equal to x, and x is less than or equal to b. So as you can see, and of course, the notation for open interval is parentheses. And it looks the same as an ordered pair. And you have to use the context in that case to determine which is which. But now we're going to turn our attention to the following. We're going to talk about subsets. Now I want you to consider what you see on the board. If you think about A and B as sets, we use that symbol. It looks like the U, sort of the flat U with the line under it. We say that A is a subset of B, or if you're feeling a little bit more elegant, that A is contained in B. If every element of A is also an element of B, and we use this expression that you see there, A and then that U with the line under it symbol. But occasionally, for the sake of variety, we might write it the other way around, right? We might write B and then sort of the U facing the other way. But let's not get distracted by the notation at this point in time. We all know what this means. Now, here comes the interesting part. If A is a subset of B and A is not equal to B, then A is called a proper subset of B. And it's the mathematical equivalent of saying, you're in the club, but you're not the president. Sorry, A, you may have a place in the set, but B still rules the roost. And with this in mind, the whole point of a subset is really very straightforward. If you want to prove that A is contained in B, your task is very simple. You have to show that if X is an element of A, then X is an element of B. Yes, it's basic, but proving a subset is as easy as showing that every member, A, has to meet the defining condition of B. the one thing that makes B what it is, as clear as the line between right and wrong in any decent set. Now, you have to show your work because A must satisfy the rules that B set forth. There are no loopholes, no exceptions. It's just pure, unadulterated mathematical logic. Couple things, preliminary things, before we get into the final proof for the video. But the first thing that you have to consider is that in a set, the order does not matter. In other words, see if I can, where's my document here? There we go. In other words, if I told you 1, 3, 5, and that can be contained in the set 1, 2, 3, 5, and 7. Why? Because 1, 3, and 5 are all in that other set 1, 2, 3, 5, 7. Right? Likewise, interestingly enough, the natural numbers are going to be contained in. I wanted to mention something also. I mentioned this earlier, but I put a little footnote here where it says A is contained in B. It looks like a cross symbol because we need to have a special note of that. Because when if is used in a definition, we normally understand it to be to have the form of if. Sometimes it's spelled IFF. That is, that we are defining A contained in B to be the same as every element of A is an element of B. So essentially, what this means is a definition that is used to establish, it's really an abbreviation for a particular idea or concept. It would be more accurate if we used if, IFF, between the concept and the abbreviation. But it's really a common practice to simply use if. So I want to clear that up. The other thing is that I think you're going to find interesting. These are all examples of the subcategories. 1, 3, and 5 is a subcategory of 1, 2, 3, 5, and 7. Also notice the natural numbers, the integers, the set of rational numbers, the set of real numbers, and if you know the complex numbers, it includes, these are all examples of that. But on the other hand, A, B, C, that is not a subcategory of A, B, E, F, or a subset, I should say, not subcategory, a subset, A, B, E, F, and G, because A, B, and C are not all contained in A, B, E, F, and G. So I just wanted to clear that up a little bit. Now, for the final statements. All right, now to prove that A is contained in B, we need to understand that every element of A is also an element of B. That is our starting point. So I'm just going to do a little direct proof. We can assume that we're going to let X be an arbitrary element of A. And if that's the case, we need to prove that X is an element of B. All right, now, we said that X is an element of A, and we are assuming A is contained in B because of the definition of subset. So that means X must also belong to B. So basically, since X was an arbitrary element of A, and we already said that X is an element of B, you can conclude that all elements of A are also elements of B. And that would sort of complete the proof. But another way you can look at this is, so we can say that a proposition, remember we talked about propositions. Proposition, we could say A is contained, I'd rather just write it out, in B. So we need an explanation of what X is an element of A means. And from that, it could be anything. Well, any explanation. Algebra, what techniques it involves. So once you have this explanation, you can say, oh, that's what X as an element of B means as well. And therefore, X is an element of B. And since X is an element of A, it implies that X is an element of B. So it follows from that that A is contained in B. But if you still don't see it clearly, we're going to do it in the next video. I'm going to show you some concrete example with the set of numbers that we'll do. But this is all I have time for today. May you all have a blessed evening and or whenever you watch this video. And thank you all for the continued subscriptions, for the support you have shown to this channel. I am so pleased that there are so many young people interested in truth and interested in defending the new ways of looking at mathematics, the rigorous way, and going back to the fundamentals. Thank you all.